Hello, I'm Carlos Rosso Suarez and this is the CRS channel. In this video we're going to continue with the geometry problem that says for a circle circumscribed to a triangle, the product of the lengths of any two of the sides of the triangle is equal to the product of the diameter of the circle and the altitude or height traced to the third side. Okay, in the previous video we worked on the case for which the circle was circumscribed to a right angled triangle, which was this case. Now we're going to work on the acute angled triangle case. Okay, so our acute angled triangle in this case is triangle GBA. Okay, to work this problem out, we're going to consider several other triangles that we have drawn here in this figure. Right angled triangles are in triangle GB, G prima, in which the segment G prima is the diameter and is also the diameter of the circle and is also the hypotenuse of triangle GB, G prima. We also have right triangle GA, G prima. We have other right triangles such as GBE, BEA, ADB, ADG, GFB, and GFA. The height or altitude for triangles GBE and BEA is segment BE, which will be labeled as H sub B or HB. The height or altitude for right angled triangles BEA and BEG is segment, for right triangles DAB and DAG, the height or altitude is segment AD, which will be denoted as HA, or H sub A or HA. And for triangles GFB and GFA, the height or altitude is segment GF, which will be labeled as H sub C or HC. We also have other triangles like BCG. We're going to show that this triangle is isosceles. Remember that segments CG, CB, CA, and CG prima, their length is equal to the radius of the circle. So triangles BCG, ACG, BCA are all isosceles triangles because they have two sides that are equal. In the case of GCA, CA and CG are equal because their lengths are equal to that of the radius of the circle. CG and CB are also equal, and CB and CA are also equal because their lengths are all equal to the radius of the circle. Okay, the angles of triangle GBA are GBA, which is angle beta, GAB, which is angle alpha, and BGA, which is angle gamma. Angle gamma is divided into two angles, which are gamma 1 and gamma 2. Gamma 1, which is angle BG G prime, and gamma 2, which is angle G prime GA, also are in the case of gamma 1 is one of the angles of the right angle triangle GBG prime, and BG prime G is another angle of that triangle, which means that and is denoted as theta 1. Okay, so we have that theta 1 and gamma 1 are complementary, and for triangle GAG prime we have that G prime angle G prime GA is angle gamma 2, and angle GG prime A is angle theta 2. So gamma 2 and theta 2 are also complementary. So those are the most important triangles to be considered in this problem. So let's see what information we can obtain from these triangles. Okay, so first let's consider triangles G, B, E, and G, and and B, E, A. They have a common side, BE, which is HB. Okay, here we have that, and we can also consider triangles GBE, BEA, as well as DAB and DAG. Okay, so let's start with the angles. Let's find the trigonometric functions for the angles. Alpha is such that sine of alpha will be equal to, if we consider triangle GFA, sine of alpha equals HC over B. Now, if we consider triangle BA, sine of alpha will be equal to HB over lowercase c. I forgot to mention that lengths of the sides of triangle BGA are such that the length of BG is lowercase a, the length of GA is lowercase b, and the length of BA is lowercase c. So again, sine of alpha equals HC over B, sine of alpha equals HB over C, lowercase c. Sine of beta, considering first triangle BGF, equals HC over lowercase a, and considering triangle BDA is equal to HA over lowercase c, or HA over c. Okay, in the bigger right-angled triangles, we have that sine of theta 1, that is considering triangle BGG prime, sine of theta 1 equals lowercase a over GG prime, which is D, which is the diameter. And for triangle G prime A, sine of theta 2 equals lowercase b over GG prime, that is b over D, or b over the diameter of the circle. Okay, we're going to continue this problem in the next video.